not sure which microphone it's using. I suspected it may be those, so maybe he's going to take me a couple of days to get the audio working good. Hopefully you're in the right place. This is actually two classes are sitting in here right now. There's Civil Engineering 433, which is Hydrologic Engineering, and then there is also Environmental Engineering 670, Hydrology and Drainage Control. And the two courses are similar enough that we'll be sharing common lectures and some assignments, although the graduate course has a separate project requirement that the undergraduate course does not. So let me hand out the syllabus a little bit later, but let's begin by talking about hydrology in general terms. Let me dim the lights just a little here. So let's talk about what is this class. We've got kind of a variety of students in here. We have some people who have already taken hydraulic engineering before, Civil Engineering 331, and then some people who are taking it just this semester. And that'll be fine. You won't be at a disadvantage for not having finished 331 yet. But this course is largely related to the water cycle and how it interacts with the environment. So this picture, I don't know where that is. It kind of looks maybe like the Pacific Northwest to me, Oregon or Washington maybe. But I like it because you know, it's so lush and vegetated, and I kind of wonder what's at the end of that path. You know, I want to go explore that because it looks like a really beautiful watershed. And so this course is about how when it rains, a certain amount of the water is infiltrated into the ground, and a certain amount of the water runs off. And it's not just about the amounts, but it's also about the timing, how long it takes between when it begins to rain and when you see runoff. And so that's kind of the essence of hydrology. And if we were going to distill it into a big question, there are a couple of different subpoints that we have to investigate to look at that big question. Anybody recognize this scene?
Yeah,
Is that a view you've seen before?
Yeah, it's right next to Calamities. That's Halgreer and 3rd.
Yep, Halgreer and 3rd Avenue. So Calamity J is on the left. This is Smith Music Hall. And this is a parking lot that many students park in. And you're not supposed to. That's a faculty parking lot, I'll have you know. But anyways, yeah, I took this picture in the spring. I mean, this photo isn't that old. I took it with my camera phone as I was doing what you're not supposed to do, which is driving into standing water. I could kind of tell it wasn't that deep, at least the part where I was going to drive. As long as you stay in the center of the lane, I could tell it was relatively shallow, but there were some spots where it definitely was not shallow. I've got another picture of a car where the water had to have gotten inside the passenger compartment. So I'm expecting that car maybe had some serious water damage. Why did that happen?
Huntington has a poor drainage system for water.
Huntington has a poor drainage system for water. That's definitely part of it. Why is it poor?
It's out of date.
It's out of date. It was built more than 100 years ago.
The elevation of Huntington, all the other water runs down to Huntington from the mountains.
Okay, Huntington is a low point. That's true. You know, you think about there are neighborhoods up on the hills. You know, Beverly Hills, which is kind of a funny name, but you know, it's some neighborhoods that are up in the hill areas. Then a little bit further west of Beverly Hills is even more like kind of wealthy, ritzy homes uphill from the park. And all of that drains towards Huntington. And there's been a lot of development up in the hills in the years since they put in the drainage pipes in Huntington. And so those pipes were put in the ground, in some cases more than 100 years ago. And the size of the pipe, they decided how big to make the pipe before they knew how many people were going to be living up in the watershed upstream. And they didn't know exactly how much roof area there was going to be. They didn't know how much asphalt there would be. And anytime you replace grass with asphalt, there's going to be more runoff, because obviously grass allows the infiltration of water to a greater degree than asphalt does. And so actually anything that human does to the soil is going to make it worse from the perspective of hydrology. We're going to make flash flooding more likely anytime you develop it whatsoever, because disturbed soil infiltrates worse than natural soil. When you remove even just raking leaves, the leaf litter will reduce the speed of water from when it rains to how quickly it's going to get to the point of concentration. And so human development is what we're trying to undo in hydrologic engineering. Hydrology is the study of the science, and then the engineering is applying tools to solve the problem. And so this course, it's a little bit unusually named. Most of the times classes were just called hydrology. But I changed the name a few years ago to hydrologic engineering because we spend a bit of time looking at solutions in this class and solving the problem. So here's a photo of flooding that is a little bit close to home, and it's in part because this is a low point. This is where it's really flat and all of the water drains to this low point. And of course, we haven't even mentioned the fact that we're right next to the Ohio River. And so the city of Huntington is protected with a concrete flood wall. And if that concrete flood wall wasn't there, we'd be at a risk of potentially flooding from the Ohio River. They haven't had a lot of use for the flood wall since it was installed. Occasionally they'll put the gates up, and in fact, I've got pictures and video of that too, where the water's just about up to the flood wall. But this is a different type of flooding than what's depicted in this picture, which I took in August. So this isn't a flat area. This is this is out in the countryside where it's a little bit more hilly. And this is just what you would see when it's lightly raining. I climbed down into this area on a day when it was just sprinkling. But what I'd love to have done, I should have gone down there yesterday when it was raining really hard. Because I would suspect it looks a little bit different. This is an ephemeral stream, and maybe that's a word you've heard before, maybe it's one that you're not familiar with, but ephemeral means that it comes and goes. And an ephemeral stream only has water flowing through it when it rains, or immediately after it's raining. And so the problem with this ephemeral stream, this one in particular, is that someone built a house in the path of it. And so there's a risk of flooding here, not because it's a low-lying area. You know, this is not a case of water backing up in a creek, and so there are flood risk maps that you can look on the FEMA website. They're called a FIRM, F-I-R-M. And those the FEMA flood maps are used to purchase flood insurance and what rate you're going to have to pay. And this person would have a really low flood insurance rate. They wouldn't have to pay much because those flood maps only take into account how close you are to a low-lying area, and they kind of are blind to the risk of flooding from ephemeral streams. And so it's not easy to see in this picture, but there is a little bit of a pipe there, a buried pipe. I think it's an 18-inch pipe. But there are going to be times when the flow from this watershed exceeds the capacity of the pipe. And so then water is going to be flowing over the surface of the land towards this home. So we're going to look at these questions of flooding and risk through the semester. And the purpose of this course is to look at a big question. And so think about, just based on what I've told you so far, what might be, if we were going to try and distill it down into a single big question, what do you think that big question would be in surface hydrology?
How to control the water.
Okay, how to control it. That's as good a guess as any.
think you said something that has to do with the man-made portion of the watershed. And
Okay.
what we need to do to mitigate that.
How to mitigate the increased flooding risk from development, that's a great observation. Any other thoughts? What do you think this course as a whole could be about? If we take a step back even a little bit further, for a certain area, what are the runoff characteristics? So we want to know how much water there's going to be and when it will be arriving. Because if it's a large volume of water, but it's spread out over a really long time, then that may not be a problem, because the pipe could potentially accept all of the flow that needs to be accommodated if it's spread out over a long time. But if it's flashy, meaning that it's arriving to our area of interest really quickly, then that's problematic. So, if we break this down into further issues, like how do we characterize runoff? So characteristics means timing and quantity. Then part of this semester, we're going to just be talking about rainfall. And I think most of you probably know that I used to teach over in the United Arab Emirates in Dubai. And ironically, 3 years in a row, when I taught rainfall, it rained that day in the desert. So it was like just this beautiful coincidence. I have the ability to make it rain in the desert by giving a lecture on rainfall. That's like 3 out of 4 years I was over there, it rained on the day I talked about rainfall. I don't know if that'll be the case here, and it's not so special. You've seen what it looks like to rain. It rained yesterday. I was out in the rain for a few hours yesterday. So some of the things that we're going to look at is return period and the amount of water that can be expected in a single place for storms that are defined by how frequently they come back around. And that's kind of an interesting thing about rainfall, is that you can talk about a rainfall amount in terms of inches or centimeters, like the depth of precipitation. But another way to describe the rainfall is by, for a certain storm, how often is that storm going to come around? And so yesterday's rainfall may have been, half an inch. But we see storms like that all the time. In hydrology, what we're really worried about is a storm that's so big it only comes around once every 10 years. And so we call that the 10-year storm. It doesn't mean it lasts for 10 years. It just means it's a storm of a certain size that comes around once every 10 years. A probability in any 1 year of 10%. And so there's a 10-year storm. A 50-year storm means that in any given year there's a 2% chance that that storm could come around. So we'll talk about return periods, temporal distribution. This is a $5 word, where if you can use the phrase temporal distribution in a sentence, people will think you're really educated and that you've really done something with your life. Temporal distribution just means how does it vary during time. And so rainfall doesn't immediately begin, stay constant, and then immediately stop. You know that when it starts to rain, at first there's just a sprinkle. It comes really slowly. And then there's a period where there's a deluge and it's raining really hard, but then it slows down a little bit. You probably had the same experience as me, where you're standing at Walmart and you're listening to the rain on the roof and you're thinking, I don't want to go out to my car yet. But if I wait 10 minutes, probably it'll slow down. And it always does. It always is going to slow down, and then you won't get so soaked. If you just are familiar with this idea of temporal distribution. Spatial distribution is talking about some spots it rains more than others. And so if we're measuring the rain over at the airport, that doesn't necessarily mean that it's going to be raining the same here in Huntington. Because the airport is, I think from here, maybe 11, 12 miles away. And so there's going to be variation through space. So we'll spend a portion of the semester talking about rainfall. We will talk about a couple of models, numerical models, that describe infiltration. That is, what fraction of the precipitation gets down into the soil. And so some of the things that we're going to have to investigate to predict infiltration is the different types of soil, because sandy soils allow water to infiltrate differently than clay soils. What do we mostly have in West Virginia? Sandy soils or clay soils? Clay. We've got horrible soil in West Virginia. That's part of the reason why we have such flooding problems. It's because it's really steep, and we have a lot of clay and plastic soils. So like if I try and plant a tree in my yard, it's mostly just rock and clay. I'm digging through rock and clay. And so antecedent moisture is another thing that we are going to talk about, and that is just soil isn't always starting off with the same baseline amount of moisture. You have to consider not only today's storm, but all of the storms in the past month to understand how ready the soil is to accept additional infiltration. So we're going to look at a few models for quantifying the effects of infiltration. There are these things called abstractions, and abstractions are just anything that reduces the amount of runoff that isn't infiltration. So it's these other factors. So for example, have you ever stood under a tree when it's raining because you didn't want to get wet, so you went under the tree? What trees are doing is they're intercepting the rainfall. And so there's less effective precipitation under a tree than is falling on the tree itself. And trees aren't the only things that do interception. There's also buildings will intercept rainfall. So that if there's a little bit of wind and the rain is coming at an angle, you could stand on the leeward side of a building and not get wet. So we have to account for things like evaporation and interception and puddles to know how much water is going to flow off of an area. We have to say how much precipitation was there, how much infiltration was there, and then these other factors that reduce the amount of water that will be flowing off of an area and towards a point of concentration. And so with these fundamental factors kind of figured out, then we move into the more engineering aspect of things. And so you could say on the left, this is science, and then on the right, we're getting into the problem-solving aspect. Runoff modeling is just trying to predict the amount and timing of water that comes out of a watershed. And so there's a whole lot of different models that we can use. Some of them are computerized. Some of the models are just manually set up. And what we're trying to get out of a runoff model is a hydrograph. A hydrograph is a graph of water, as the name would imply. Hydrograph. It's just telling you the time on the horizontal axis and on the vertical axis, the runoff quantity. And so that's what you get out of a runoff model is a hydrograph. And you use that hydrograph to figure out, well, if water is going through a stream channel that causes delay, that's routing. Routing is the effect of water moving through the environment, how much time it takes. For example, if water is flowing as a sheet and it's just going over the surface of a parking lot, there are equations we can use to calculate the velocity of the water's flow as it flows as a sheet, and then it's going towards a ditch, because all of that delay we have to account for. As the water flows through the ditch, what velocity is the water experiencing? And how long does it take to get downstream? So that's routing. And finally, the implications is, how are we going to deal with this water? Do we need to build a pond to accept it? Do the channels need to be sized a little bit differently? Sizing of culverts, sizing of flumes. So you can think of this as an overview of the course, how we're going to be spending our time this semester. And a lot of it is science. There's a reason why this course is not a design elective. It's a civil engineering elective, but not a design elective, because we're going to be spending quite a lot of time in the science side of things. And in my past experience, sometimes engineering students, once they get to be seniors or graduate students, they think, oh, science is behind me. I already did chemistry and physics. They're more just in the habit of engineering and calculations and problem solving. But I mean, there's just going to be some memorization. You're going to have some terminology you have to memorize and know, concepts. So proportionally more of this class is about conceptual understanding versus problem solving compared to some of the other classes you may have had from me in the past. So any questions so far about these ideas? Okay, so here's our announcement slide for today, and I'm going to post these lecture notes online, assuming I can figure out the new version of Blackboard. I logged onto it this morning, and the only thing I could see was like a message center. I didn't see anything else. So I'll get that figured out, I hope. And so I'll put the lecture notes, but what you need to do between now and Wednesday is download a program called HY8. I'll show you the link to that in a minute. If you just do a Google search of HY8, it'll come right up. This HY8 is free software that's put out by the Federal Highways Administration. Like every program you use this semester, it only works on Windows. There isn't a Mac version. So you're going to need to borrow or have, or just have access to a Windows computer to run. I think there's probably 4 programs we're going to use this semester, and they're all for Windows. All right, let me hand out the syllabus. Yeah, so here's where you can find, here's the link to HY8. If you just Google download HY8, have that downloaded and installed for Wednesday, because we're going to work an example together in class on Wednesday. So bring your laptop with HY8 installed. All right, so here's the syllabus. Okay, let's take a moment to go over the syllabus, just briefly. I mean, you've seen syllabus before, and you've seen them from me, so I'll just maybe point out the highlights. My office hours are on the first page. Monday, Wednesday, Friday, from 11 to 12 and 2 to 3. And if you need help outside of those hours, you're welcome to stop by my office, and if I'm available, I'll help you. You can also send me an email or contact me on Teams. Like if you have a question on a homework problem, probably the most efficient way to get that question answered is to come see me in person. And the second most efficient way is to call me on Teams. And the least efficient way to get help is to send me an email, because like I can't ask a follow-up question, it's harder for me to see what you've done. So email is maybe the worst way for us to sort out things when you need help. So I really prefer like a live interaction, because then maybe you could share your screen with me and I can look at what you've done. Everybody here hopefully has already filled out the 2 COVID things you have to do this semester. You've got to do a return to campus agreement and also the vaccine registry, right? So in the next day or 2, if you haven't done that, they're going to drop students who haven't completed it. The textbook info is here on the 2nd page, Water Resource Engineering, 3rd edition by Larry Mays. I'd encourage you to get a copy of that book. The homework assignments are going to be not from that textbook, but reading assignments will be, and there's certain terminology that I'm going to ask you to learn that I'm not going to lecture on in class. And so I'm going to give you a list of phrases and words that you need to know, and you can find the definition to all of those phrases and words in the book. Also, you know, I'm trying to show you both hands-on software stuff and examples, but there's additional reading material in the book that if you really want to know this stuff, you need to read the book. If you're just here for a grade, maybe you could get a C or something if you don't buy the book. But if you buy the book and you really put the time into reading it, then you'll get a lot more out of this class. You can see the course outcomes are listed in the next table. I'll have a schedule for you on Wednesday that shows the outline of which days we're going to cover what lecture topics, and assignment due dates. The tentative assignment due dates will also be on that schedule. Note that there is here in bold a statement about how the software we use in this course is only available for Windows. It's not available to work on the Apple operating system. Okay, the grading policy is shown with the breakdown of percentages and so on, and I'm going to be taking attendance this semester, and so the way that that'll work is 10% of your course grade is determined by attendance, and each unexcused absence that you have is a 1% reduction. So basically, if you had 2 unexcused absences during the semester, then that means you get 8 out of 10 of those attendance percentage points. So I guess that means I probably ought to take attendance here before we go our separate ways. My late work policy hasn't changed. I don't accept late work unless it's a university excused absence. My expectations for academic integrity are that you do homework assignments and exams and everything else. When you submit work, it should be what you have done. And it's okay to talk about assignments and discuss concepts with other people. And if you've been doing your work and you need help finding a mistake, it's okay for you to get that help from a classmate. But there's a fine line between what's acceptable behavior and unacceptable behavior. And so I'd ask you to read through the entirety of that academic integrity statement and let me know if you have any questions. Okay, so that's all I've got to say about the syllabus. Please read it in its entirety. Do you have any questions after having looked it over? Let me know if something comes up that you want to ask about. Okay, so let's get into some of this technical material. Part of this course is devoted to hydraulic structures. The first part of the class, we're going to be learning about flumes and culverts. So those of you who've already done Civil Engineering 331, this kind of picks up where we left off. And for those of you who haven't done it yet, this is going to be, it follows after some of the other hydraulic structures that you'll learn about in Civil Engineering 331, but none of what you'll be solving has as a prerequisite that other material. So where we leave off as far as hydraulic structures goes in hydraulic engineering is talking about broad-crested weirs. And a broad-crested weir is a hydraulic structure that's used to quantify flow. It doesn't regulate flow. So a broad-crested weir doesn't change how much water is going through a channel. It simply is something that's used to measure the flow rate, because you can't just look at water flowing through a stream or irrigation canal. You can't just look at it and know, for example, how many cubic feet per second that is. You have to have different ways of measuring the flow. And so what a broad-crested weir does is there's this step, the water has to flow over the obstruction, and when it encounters an obstruction with a certain height, then the water will flow over the obstruction at a depth that's known as the critical flow. And so basically with a broad-crested weir, once you have that critical flow depth, you can use it to find out the flow rate through the entire channel. So this is not an equation you're going to be solving today or in the future. I just wanted to show you this to set the stage for a flume, because a flume you can think of as satisfying the same objective as a broad-crested weir, but it has a couple of advantages. Because the problem with this broad-crested weir is that trash will accumulate upstream of the obstruction. So sediment and debris could accumulate because you've got this basically obstruction in the flow. And also what it does is it removes a lot of energy. So it's kind of inefficient from a hydraulic standpoint. There's head loss through a broad-crested weir. So more than 100 years ago, someone invented a better way to measure the flow rate. The whole purpose of this device is to quantify Q. And so what this other device is a flume, and whereas a weir has head loss and deposition concerns, and it works by being an obstruction that raises the bottom of the channel. So it's a contraction in the channel just by making the bottom higher temporarily. A flume contracts the channel by making it narrower. Instead of raising the bottom, it makes the channel narrower. And what the advantage of that is that it avoids the deposition, has less head loss, and so it's just a more efficient way of quantifying the flow rate, satisfying the same overall objective. So here's a side view, and I found a video today of a partial flume. You may hear this word partial. It sounds like the word partial, but it's not. Partial was the name of a person who invented this flume. So a partial flume is this device where water is flowing through a stream, and then the channel gets narrower. So this is here's the flow. So upstream, the water's flowing in this direction. So the channel gets narrower, and then the water flows down a hill, and it forms a hydraulic jump because it got narrower and it flows downhill. And then the hydraulic jump occurs in the diverging section where the channel is getting wider again. So this video just illustrates briefly. Once we get through the commercial.
I thought for sure you'd have premium YouTube.
Oh, I should, right? Okay. So here's the video. Let me dim the lights a little bit. They're using a recirculating pump. So you can see the water is coming from this side on the right towards the left. When they turn on the pump, it's sending the water back up to the top here. So the water is going through, the channel's getting narrower. Then there's this constant width section. Here from the top view you can see, but it's downhill. So the water is accelerating as it's going down this hill. It's getting some velocity, and it's supercritical. And then it goes through this transition of having a hydraulic jump. So what Partial realized was that if you measure the depth of the water at two locations, then you can quantify the flow rate. So there are these calibrated empirical equations that simply relate the depth of flow at two spots to the flow rate. Let me pause for a second here and talk us through. Now, if you haven't taken 331 yet, you haven't heard about supercritical flow, but you can just think of it as the water is moving very fast. The water is moving very fast. It has a relatively shallow depth, and then it goes through this transition called a hydraulic jump. And maybe you've seen a hydraulic jump in a river before. Like if you've ever been rafting on the Gauley River or the New River, sometimes boats will kind of, they'll go down a fall and then try and swing around like behind a rock. And you can kind of surf in place, either in a boat or sometimes people will surf in rivers, like on a standing wave. That's what this is it's a standing wave. And so by measuring the depth of flow in this flume, you can quantify the flow rate. So let me go back to this diagram. The two spots that you would measure the depth of flow in the partial flume would be in the converging section. You'd measure the depth at location A, where the water is just starting to come together, and you can see that it's 1/3 of the way into the converging section, or 2/3 of the way before you get to that constant width throat section. And then towards the end of the throat section, you'd measure the depth again at location B. With these two depths, there are different equations depending on how wide the throat is. And so here you can see this term W is referring to the width of the throat section. And so there are these different equations for how wide the throat is. And partial flumes are oftentimes sold by like agricultural supply companies or precast concrete manufacturers or plastic manufacturers because they have these flumes that are just plastic and you can move them from ditch to ditch. You know, like if you're a farmer and you're trying to figure out how much water comes through your irrigation canal. So every manufacturer of these flumes will have a calibrated equation similar to this. And the flow rate is usually just based on the depth upstream prior to the flow through the throat. But the reason why we measure that throat depth is to know whether the hydraulic jump is submerging, whether the tailwater is submerging the hydraulic jump. Let me just go back here for a second. All right, so where's a good view of it? Sometimes what you've got downstream is a channel that it doesn't have enough flow rate to get the water out of the way of this hydraulic jump. Like if you have a really shallow channel downstream, it might be that the water downstream is backing up and you don't actually even see the hydraulic jump. They call that a submerged hydraulic jump. And there's a certain threshold by which you can measure the submergence criteria to know whether you have free flow or not. So these equations, you see it says free flow capacity. You'd use this equation, and if there's plenty of capacity in the channel downstream and the hydraulic jump you can see and it's not drowned, then it's really simple to find the flow rate. You just put in the depth of flow, and you can tell that this is an empirical equation and not a fundamental equation because it has these very strange, like, coefficients in front of it. You know, 0.31, 381, 0.535. I mean, there's nothing, like, there's no law of physics that this is derived from. It's just curve fitting. They observed a lot of different situations where they measured the flow rate, they measured the depth of water, and then they found like a curve fitting factor that would bring it all together. So there's both this exponent factor and the coefficient in front of it. But like I was saying, sometimes this hydraulic jump you can't even really see very well because the capacity of the stream down, the capacity of the channel downstream is poor, and so you have to check the submergence. And so you measure the ratio of the downstream depth to the upstream depth. And there's this submergence criteria. And if the depth of flow downstream is above the submergence criteria, then you have to make a correction. So you'd still use these equations, but then you'd adjust the flow rate because the flume isn't going to be able to carry as much water if the hydraulic jump is drowned. So the way that you do these corrections, if this is exceeded, if you're over the limit, you don't have free flow, is you would find out what is the upper head, H sub A, and you'd look at this ratio of submergence, and then you'd go down to a correction factor. So you're basically using this nomograph. You're going to look up the correction in terms of cubic meters per second. And this particular curve is for a specific throat width. So you can see here that this is for a throat width of 0.30. Sometimes you won't have the curve for the throat width that you need. And so you can extrapolate with this given nomograph to other widths, to other flume widths, by multiplying the correction factor by the correction that you see. So then the overall flow rate would be the free flow Q minus this delta Q. So we're going to practice this in class on Wednesday. We'll do an example with a partial flume calculation. Okay, so before we go our separate ways, I need to take roll, because I'm doing that this semester. Let me just stop the recording and then we'll go through the class roll.